upload and
Right. Okay, cool. Got the recording. Let's start. Um. Okay, so we're gonna start with decree theory, and specifically with definitions. So everything is gonna be happening on the sphere. So imagine we have a map from, whoa. Okay. From a sun to itself. And the whole point is that if we look at the pullback of this map, F star, then it goes from chain of Sn to itself. Well, how do I stop this? Okay, cool. So the idea is that both of these spaces are actually Z, and that means that F star has to be like a multiplication by some number. Then there exists like a integer number, so that F star alpha is actually T alpha. And okay, well, the definition is going to be that this D is called the degree of the map F. Okay, cool. So I'm gonna state just some properties. Most of them are like really simple and even easy to prove, but I'm not gonna do that. So the easiest map is just the identity map. Its degree is gonna be 1. Just because if F is ID, then F star is also the identity operator, so D is equal to 1. Then like a nice thing is that if F is not surjective, then the degree of F is going to be equal to 0. That has something to do with the excision theorem. Basically, we just can throw away the points where like outside of the image of F and apply the excision theorem. Then if two maps F and G are homotopic, then they have the same degree. So I guess degree is homotopy invariant. The next thing is that degree, the product is the product of degrees or composition. And then maybe more specific examples. So we have already had the example of the identity map. Then if we'll consider the antipodal map, so basically we just map x to negative x, then the degree of that is going to be -1 to n+1. And then if F is a reflection, that would mean that we just, I guess, change the sign of one of the coordinates. Then the degree of F is -1. Okay, and the last property is that if f has no fixed points, and the degree of f is -1 to the n. The idea behind this is that if f has no fixed points, then we can find homotopy equivalence between f and the antipodal map, basically by doing, whoa, six. Negative x. So we can go from x to negative x. No, wait a second. We can go from f to negative x through this line. And this is possible because these 2 points are not antipodal. So everything's well defined. Okay, then here is a first nice application of degrees is Heriot theorem.
Wait, what? When you define can you scroll up to the previous property?
Yes.
The degree, it looks here like the degree of the antipodal map is -1 to the n plus 1. But down there you wrote degree of f is -1 to the n.
Yeah, that's definitely what I meant. Thank you.
Yeah, and one way to remember like what the power should be is to use the reflection property. So like the reflection is -1, and you have n plus 1 coordinates because Sn sits inside of Rn plus 1. So using that property, you can remember like if it should be n or n plus 1.
Yeah, right. Oh, this is annoying. Okay, Heriot theorem. This is something I think we have covered in like both geometries probably, but I'm gonna say it again. So, okay, it says that Sn has continuous non-zero vector field if and only if n is odd. Okay. Let's quickly try to go over the proof. Okay. So I guess one way to go is, or going one way is as if the sphere does have a continuous non-zero field, if x continuous vector field, and then v is not equal to 0, then we can normalize f. Normalize v, sorry. We just divide v by its norm. So after that, we can suppose that v is of norm 1. And then I guess after that, what we can do is from every point X, we can move to the direction of V X to get to negative X. So you can write this formally, but there's the vector X, there's V of X, and we're just going this way. And this is going to define homotopy equivalence between X, between ID and negative ID. And then we know that degree is homotopy invariant, so degree of ID, which is 1, is equal to degree of the antipodal map, which is -1 to n+1, which proves that n is odd. To go the other way, it's kind of simpler. If n is odd, 2k minus 1, then our sphere Sn lies inside our n+1, which is our 2k, and then define V to be a map that goes from X. And then with every 2 coordinates, we just swap them and change the sign of one of them. Then V is continuous. And then V of X is perpendicular to X, which means that V is a continuous non-zero vector field. So we're good. Cool. Okay, so we're gonna do another application of degrees, which is the following proposition. So if n is even, oh no. Suppose n is an even integer. In that case, so the only group G that acts freely on Sn, which is not trivial, is G equals Z2. So if we have the only group that acts freely on Sn that is non-trivial is Z2. And by saying that it acts freely, we're basically just saying that whenever the element of G is not trivial, the action is not gonna have fixed points. So for the proof, we again need to do 2 ways. To go this way, so if G does act freely on Sn, then for every non-trivial element of G, we have that well, the action of G on Sn doesn't have fixed points. I'm gonna denote it as a scalar multiplication. Doesn't have fixed points. And that's the point where we could use one of our properties, specifically this one, the last one. So since the action of D doesn't have fixed points, it means that the degree of the corresponding map is going to be -1. Also, so we have that for non-trivial elements, the degree is -1. For the trivial element, our degree is going to be 1, just because it's the identity map. So we get a map from G to degree of G. So the idea is that we proved earlier, or I guess just said earlier, then that the degree of the product is product of degrees, which means that degree is an isomorphism between G and G2. And the reason for that is because it's linear, and then, or I guess homomorphism, and then its kernel is trivial. Yeah, we were doing this strange representation of Z2 that's like multiplicative, just -1 to the power n, I guess. Okay, so what we got is that if G does act freely on Sn, then we define this map degree, and it's gonna be an isomorphism between G and Z2, which means that G is basically equal to Z2. And going the other way to show that Z2 does act freely on Sn for G equals Cn2, it's enough to just consider ID and negative ID that are going to be the actions of Z2 on Sn. Do you guys have questions?
Could you really quickly show the statement of the proposition again?
Yes. No, wait. This one. Okay.
Okay, awesome. Thank you.
Okay, let's move on.
Oh, I had a question.
Yes.
So the argument you just gave for like why something without fixed points doesn't or has degree -1, could you use that to say that not just like an automorphism of the sphere, but like any map from the sphere to itself that doesn't have fixed points has degree -1?
Yeah. Yeah, that's what we did. I guess.
Oh, right. Sorry. Yeah, you said that.
Here, yeah.
Yeah.
Yeah, it works right now. Maybe other questions? Okay, cool. So there is really a lot of stuff, but next thing we're gonna do is, well, how to actually compute degrees. Because the definition we had is kind of nice, but also very hard to use to actually compute stuff. And then the other thing is that we had like a different definition of degree in plus quarter. And for now, it's not really similar to what we have, but I'm going to show that it's pretty much the same thing. So again, we have a function f that goes from Sn to Sn. So suppose we have a point y in the image, and that its pre-image is finite. Then we're gonna look at f locally. So what we can do is we can find neighborhoods around xi and a neighborhood around y, neighborhoods such that f, or the restriction of f, maps Q's to V. And we also want them to be disjoint. So then, since we can restrict V to UI, we can also restrict F star. We can restrict it from HN, the neighborhood, relative to what is neighborhood to so they're doing this big diagram and stuff, but the bottom line is that both of those things turn out to be isomorphic to Hn of Sn, which is itself isomorphic to Z. So locally, we kind of have the same thing going on. So we have like a map going from Z to Z, which means that there also exists like a number, blah, 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 blah. F star is a multiplication by that number. So we can define something called local degree. So it's going to be defined, well, this way. So the local degree of f at xy, at xi, is going to be defined in the same way by the restriction f star from Hn to Hn from V. Here's why this is a nice thing. Well, a couple of things. So first of all, let's do a remark. And it's that if F is a homeomorphism around Xi, which means that there exists a neighborhood that's mapped homomorphically into a neighborhood of Y, then the local degree of F is going to be equal to plus or minus 1. And this can actually be used to compute degrees together with the following nice proposition. One, two, three. So here's how the local degree connected to just degree. If we want to compute the degree of the map F, we just need to add up the local degrees. So this is another thing I'm not going to prove, but I'm just going to say that this is already very similar to what we had last quarter. So what we had is that like we have a function F, and we're doing pretty much the same thing. We're looking at every point of a preimage of a point locally, and then we're adding up like either zeros or negative zeros depending on what the orientation is like around that point. And that is pretty much what's happening. Now we can use this fact to construct or to do the following example. So again, last quarter, there was like this problem, which was to construct a map from S1 to S1 and from S2 to S2 of any degree, basically. And now we're going to do the same thing, but for Sn. So if we have an integer number d, well, an n is still positive integer, then there exists a function f from Sn to Sn such that the degree of f is equal to d. So actually this construction is very, I don't know, I liked it so much because I remember struggling so much last quarter to like do this thing even for S2. And this is so much nicer than what I did, definitely. So let's do the construction. So we're gonna define F to be a composition of two maps. And we're gonna define two maps and then take F to be the composition of those two maps. First of all, we can definitely say that D is not equal to 0 because otherwise we can just take F to be a constant map and we're good. Then define K to be the absolute value of D, a positive integer. So now let's define those two maps, the composition, so the composition of which is going to be our F. So first of all, we have our Sn, and for the construction, we're going to use a wedge sum of K-spheres. Wedge sum So define function Q from Sn to Sn. This is going to be a quotient map, meaning that we choose his disjoint balls in Sn, and then everything. Okay, let's do different color. So everything but those balls get contracted into this one point. That's the map. And then the second map is, well, we're basically going to go back from the batch sum to Sn. And this is simpler. We just identify all of the spheres. So they all go into one sphere. Okay. Now the only thing, I guess, yeah, we now define. Where's my next? Okay. Define F to be the composition of P and Q. And then to count the degree of F, we do this local kind of thing. So take Y that's in Sn, and we're gonna look at those Xi's. The only thing is that we need to not take this Y to be like the image of this point, because otherwise it's just a mess. And it's not gonna have a finite pre-image. So take any other point. Then for the map, this is map P, and for the map P, it's gonna have K preimages. So here are the preimages here, and then for the map Q, it's just homomorphic around all of those points. So each of them is gonna have just one preimage. And then if we look at those maps, then actually around Xi, F is a homeomorphism. So the degree of F at the point Xi is either plus or minus 1. Well, that's kind of a problem, because what we want is for them to adapt to D. So we want all of them to be either 1 or -1. But we just can adjust our construction a little bit. So adjust Q by reflecting some of the spheres. So right here at this point, we could reflect some of the spheres like this. And well, everything will pretty much stay the same, except we change the orientation of I guess this map, this set around the point Xi, which will change the degree of F around point Xi. right here. Then we have degree of fxi. We can already say that it's like either 1 or -1 depending on what we want. Specifically, we want it to be the sine of t. And then degree of f is going to be the sum of local degrees, which is d. Okay, questions about this?
Maybe one thing to add is that last quarter you guys were looking for smooth maps. So that's another reason why this is somewhat easier to construct.
Oh, yeah, you're right.
Because these are, in no way smooth or obviously smooth or even obviously able to make smooth. But they are continuous. Yeah.
They're not smooth at all, are they?
And I doubt it, right? Because you're sort of crushing everything to a point. Like you're sort of
Yeah.
creating these singularities.
Okay.
Actually, I had a question related to that. So like in computing the degree, we said like suppose there's this point that has these like finite fiber or something. So there are like lots of maps that won't have that, but I can't think of any that aren't surjective. So I'm just curious if is there a surjective map from a sphere to itself such that every point has infinite preimage?
Oh my God.
Like continuous map?
Yeah, continuous. Yeah.
I feel like that would violate compactness somehow.
Yeah.
Oh, that's a very good point.
Yeah, it seems unlikely.
Okay, let's do more stuff.
Oh,
the
maybe,
next- oh,
sorry, I have another question. I don't know, maybe you mentioned this already, but when we're computing the degree of the map, right, we pick a specific point. Are there restrictions on what points we're allowed to pick? Or is it true that all points will give you the same computation?
Not that I know of. Well, they actually, like in the book, they say we want all points to have finite preimage, but then they like use this thing for this specific construction, and this specific construction doesn't have all points having finite degree or finite preimage. So I'm gonna say no that I know of. Are there?
There's usually some sort of condition on the right, like choosing a generic enough point. And I mean, in this construction, right, it's all but one point, right?
Yeah.
So I imagine there's some sort of condition. I don't actually remember. I know, right, like in differential geometry, right, we have to pick a regular value, right? So there should be some analogous thing here, right? We can't choose any point. We have to choose a regular value, and then if we do that, then we can define these degrees.
Yeah, it doesn't say anything. Oh, I'm lost. Okay, going on. Yeah, next thing we're gonna do is fill your homologies. Okay, so before we're ready, okay, I'm gonna, I guess, say that this is another way to compute homology groups, and that might, like, And this is very effective and maybe more effective than the other ones because it's easier to use. So before we're ready to actually define the way to do this homologic groups, we need a lemma. Here it is. Okay, so we're gonna be looking at a CW complex X. Okay, we're gonna consider relative homology groups X n minus 1. And actually, it turns out that we can know pretty much everything about them. So if k is not equal to n, then this thing is just trivial. If k is equal to n, then that is z to the m, where m is the number of n cells in X if k is equal to n. So for this one, I'm gonna say that in the book, they have like a slightly more confusing statement. They say that this group is gonna be like free abelian with just with m generators. And I guess like the reason they're doing it is because we can actually do homologic groups in like with groups other than z, but in the case we define it, it's just going to be z to the m. The second thing is if we look at homologic groups of xn, then it's 0 for all big n's greater than the dimension of n. In particular, that means that k of x is equal to 0 where k is greater than 1. So basically all of those things are, or I guess specifically this one, is very similar to cohomologic groups that we did last quarter. Yeah. And then the last thing in the lemma is that if we consider inclusion from xn to x, I guess here we should write dimension of x. Yeah, consider the inclusion from xn to x, and then that's going to induce the map I star from hk of xn to x. Then here's what we know about I star. So for k less than n, this is going to be an isomorphism. K is less than n, and if k is equal to n, then we don't know that much, but it's going to be surjective. Okay, so apparently the proof of this lemma is kind of important to understand, but I still want to, because it's been a lot of time. But I want to talk about what this lemma actually means a little bit. So one thing is that mm, so- okay, yeah. So what we can do is yeah. Then we can write long exact sequence for this one to then. That's one of the things that Luna did. Yeah, it's just that. Okay, let me just write it. Gonna start with hn plus 2. Gonna be h plus 1. Hmm. Oh no. Hmm. Okay. Um, with hn plus 1 xn. Right, does it seem right? Okay, cool. So the thing is, because of our lemma, some of these things are equal to 0. Specifically this thing, because it's non-zero even only if those things are 0 or equal, sorry. Then this thing is also 0. So we kind of get a short exact sequence. And then, wait a second. I'm not gonna actually write it because it's scary. Wait. But here's what they do with it. Okay. Good enough. Okay, so what is happening is we're taking, so we can do that for any n, right? And we're taking all of those short exact sequence and combining them. So here's one that we wrote. Then there is going to be the next one right here. And then also they're doing short exact sequences this way. Okay. Combine several Yeah, so what is gonna happen is we're gonna get this sequence where DNs are just defined as compositions of those maps. Yeah, so that is exactly okay. Now, by computing stuff, we can get that actually the composition of Dn and Dn plus 1 is 0, which lets us to define, well, another type of homologic groups. We just do quotients, we just quotient the kernel by the image. So this defines another type of homologies, or sorry, homologies. X. And then the reason we were doing all of this is because of this theorem. It says that this thing is actually the same as the homologic groups we already defined. So this is just going to be another way of computing them. And well, the nice thing about them is actually that we know what all of those spaces are. In the case for, they're just going to be z to the n, then z, or sorry, z to the number of n cells, which is kind of nice spaces to work with. Okay, then what we're gonna do now is just try to get a couple of things about those maps Dn, and generally about the homologic groups defined this way. So let's talk properties. So I guess there are just two. So one of them is that if X has no n cells, then the corresponding homologic group is actually trivial. That's because we have no zero cells, so we have like a 0 in there. We're just gonna have 0 space, so a subspace of that is also going to be trivial. And then, well, another very simple thing is, which also follows from what those spaces are, which is z to the m. So if X has m n cells, then Hn of X is going to be generated by at most m elements. This is again just because it is a subspace in Zm. Another property, I guess I'm not gonna write down, but sometimes when we are gonna deal with this, it's gonna be just convenient to look at what Dn's are. There are these compositions. And for example, if the boundary map is 0, then Dn is also 0. And we're gonna use it in one of the examples, at least. Now, here's how to compute those DNs. So we've got cellular. Oh my God. Boundary formula. So here's how to compute Tn of E alpha n, where this is SL. So this formula says that it can be computed as a sum E alpha beta, E beta. So this is an n minus 1 cell, and here's how we define D alpha beta, where D alpha beta is a degree of some function. This function is a composition of two functions. P alpha is a attaching map of P alpha. And then Q beta is a quotient map n minus 1 to n minus 1. This map is the map that collapses everything but the cell E beta. Your point. So this construction is a little bit difficult, I think, but basically we have a combination. So this one, and then we stick x and minus 1 in the middle. This is going to be the attaching map. This is going to be the quotient map. So sometimes we're going to need that just to figure out what the ends are. Okay. And now, before we're ready to do examples, there is one more thing that makes sense to say. So if oh my God, X has only 1 0 map, only 1 0 cell, which is the case in for a lot of spaces. So if it only has 1 0 cell, then that would mean that the boundary map is 0, just because the boundary of every one set is 0 by definition. And therefore, D1 as a combination of something with D1, the first boundary map is also going to be 0. Does this make sense? Do you maybe have questions? Okay, cool. Examples. So the first example is pretty simple. It's complex projective plane. And the thing about it is that it has no cells of odd dimension. That's going to mean that when we do our, what is it? Yeah, when we look at this sequence, half of the terms are going to be zeros. So what we're going to have is c to 2n 0, n minus 1, 2, 0. That's it. So that is going to be h of, oh my God, I'm confused.
There should be one.
Oh,
cell, right?
just one. Yeah,
Even
okay.
dimension.
Like that. So there's just one cell of every even dimension, which produces d, and then for odd dimensions, we have 0 cells, which is going to be 0 to 0, which is 0. Okay, cool. So we know what, then that will mean that all of the maps are zeros. And that would mean that Hn and I have these sets if k is even and k is less than or equal to n and 0 otherwise. Okay, does this make sense? Okay. Okay, another
But
example.
it should
Oh.
be 2n, right? K is less than or equal to 2n.
Oh, yeah, you're right. Thank you. Okay. Okay, the second example is going to be if X is equal to G, a rentable genus G surface. So what's happening is we have 1 0 cell, 2 G 1 cells. Oh my God. And then we have again 1 2 cell. That is going to mean that our sequence is going to be this. So we know again that D1 is equal to 0 just because of this remark over here. So we have only 1 0 cell, which means that our last map D is going to be 0. Yes. Right. Yep. Okay, well, and to compute D2, we're gonna look at the yeah, we need to actually look at the structure of MG. Let me do this fast. Yeah, I guess. Yeah, I'm gonna skip this and just say that to compute D2, we're gonna need to look at the CW structure. Oh my God, it's so much time. Okay. Okay, I have just one page of theory left. The next thing is Euler characteristics. So there is not much yet about this. So what's happening is for a CW complex X, we defined Euler characteristic of X. So different letters to be alternating sum of the number of M cells. And well, there's just one big thing about it. It is that there is a way to compute this through homologic groups. So X is actually, oh my God. Is equal to alternating sum of rank of H and X, and where the rank of a group is the number of its generators.
In the torsion free part or just in general?
What
Right, like you
think
can have
just in
things that
general.
look like Z, plus Z mod 2 or something.
I think it's just in general. Let me check it out.
Yeah, the number of Z summons. So you look at, you look at the
oh.
free part, yeah. And you could check this, if you compute the homology of RPN, you'll quickly see that it has to be this.
Sorry about that. Yeah, I guess it's a thing that we're gonna be able to say more about later, right? Okay. And then there is another way that's worth mentioning, but I'm not gonna spend a lot of time on. That's migratory sequence. We've done like a lot of stuff with it. So the only thing that I'm gonna say is that it is the same. And maybe write it. Yeah, so if X can be separated into a union of two subsets, or even a union of their interiors, then we get an non-exact sequence. FB X. It's 1 here of X. Okay, so the maps are here again, just as we did last quarter. We're just doing the sum of the oh no, sorry, that's not here. Here we're just doing sending X into like XX. Here we're doing difference of two coordinates in here. D blah 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 blah. So yeah, the bottom line is the same as last quarter. We're gonna do the same stuff and like use that to compute homology groups of like more complicated spaces by breaking them down into something that we know homology groups of. And then the last thing is that there is such a thing as homology with coefficients. The idea is that everywhere before we were just taking like free groups generated by something with integer coefficients, but like there is no real reason why we wouldn't be able to take coefficients from somewhere else instead of taking them from Z. So that's the whole idea.
And next week we might see there's something called the universal coefficient theorem, which actually helps you just translate from one set of coefficients to another. You do have to calculate something else that's a little algebraic, but I think we'll see it next week.
Spoilers. Billion group G instead of Z. So for example, when we were doing chains, there were sums like that, and I were integer. But in our case, we're just gonna take them from a group G. And then everything remains pretty much the same. So like they devote a lot of time to this, but the idea is take pretty much any proposition, replace C with G, and it's gonna be still true. And I guess like some of this stuff, for example, you can do over Z2. And the thing is that the computations are gonna be like much easier, but we still like get a lot of information, and that's enough in a lot of cases. That's why it's nice. Okay, let's move on to the qual problems.
I actually had
Or
a
let's,
question.
yeah.
Sorry, I just had a question about this.
Yeah.
I feel like Hatcher made some remark, I don't know if it's in this chapter or in the next chapter, about how this like isn't the same thing as taking like a free like I don't know G, like I don't even know what this means, but like a free G module or something. He says it's like not the same thing. But like do you have any idea what he means by that?
I don't think I have seen this comment.
Uh,
Maybe,
I mean, so we've sort of defined the same homology in like a few different ways, right? Like we did like simplicial stuff, we did singular stuff, we did cellular stuff. I'm not sure if his comment was directed at one of them or if it's just in general. I mean, it's probably true that other stuff changes, but I think the idea should be somewhat similar.
Jacob, did you say it is or is not a free G module? Because I would believe if it is, I kind of can't believe it's not.
He was saying it's not.
That's weird.
Maybe I just misread it.
Because this literally looks like the definition of a free whatever module. If G was like a ring, right?
Mhm. Yeah, I'm not sure, but in practice, the nice thing is that we'll use this theorem to go from Z to G. Yeah, and then just as on the chain level, you tensor it with G. Because if it's abelian, that'll be nice. Yeah, and this gives you like this like Tor term that will be in this sequence in order to go from Z to other coefficients. But we'll hopefully see more of this next week. They sometimes like to ask this on the qual, and they usually give a really easy situation where like this extra thing that you need to compute, which is like the Tor, is really easy to compute. Like it's usually either 0 or some like Z mod something.
Okay, so I just looked in Hatcher and I realized I was kind of way ahead of where we are, because this is in like cohomology. He's saying that basically you have to like, it's a little the universal coefficient theorem like doesn't really work when you're looking at R modules, like where R is a ring. So totally different thing. So
do you maybe have any other questions? Okay, let's do qual problems then. One sec. Okay, here's the first full problem. It's from spring 2019. Problem 9. Yeah, we'll only do the first part though, because that's hard. Okay, so what's happening is we have a circle S1, which is itself a CW complex. And then we're touching two cells by two different maps. This is one. This is we are touching by C to the 4, and this we're touching by C to the 7. Okay, so we've got 1 0 cell, 2, no wait, 1 1 cell, and 2 2 cells. So what we've got to do is do a long sequence, which is going to be 0, 0, then z squared, then g, then g, then 0. Okay, so this thing is going to be, this is d1, this is d2. So notice that we can still apply the same argument from wherever, from here. Oh, yeah, so we can still apply this remark because our space has only 1 0 cell. And because of that, this map is going to be a 0 map. So G1 is equal to 0 by remark somewhere there. And then for T2, we can just figure out what it is. So we take a pair A and B from here, and with the map Z to the 4, A gets sent to 4A, or A0 gets sent to 4A, and B gets sent to 7B. So that means that it sends B to 4A plus 7B. Really wouldn't even care what it is. The only thing we care about is that this is surjective. So what is happening is we're going to have 0 mapping here, 0 mapping here, 0 mapping here, and a surjective mapping here. And then we can just go ahead and compute homology groups. Two. So this one is going to be Z. First one, 0, just because we're quotient Z by Z, and then the second one is Z again. So this problem is kind of simple. You have questions?
Does everyone understand this construction? Because this is sort of like the main tool that you can use.
What's your quickest way to argue that H2 is Z? Like to see that the kernel of that map you wrote down is a is like rank 1 or whatever.
Well, just by dimension argument, right?
Gotcha. Okay.
You could also write down the kernel, right? It's like, once it's some like, what is it? Not GCD, LCM of 4 and 7, and you get a Z's worth. Or if you're Joss, I guess you could tensor with Q.
Actually, that makes sense. So it's like Q2 to Q kernel has to have rank 1. And then it's all subgroup. It's a subgroup of a free thing, so it's free.
Yeah.
Let's see another problem. Wait, let me find it first.
Maybe during this transition, I'll say, so we still have 2 open talks. I think Sam is maybe agreed to take the talk next week.
Yeah, I'm doing that.
Okay, awesome. And then there's 2 other ones. Now, if one of you wants to volunteer, that's fine. I was also thinking it's possible for me to do it like the following week after Sam's talk and just squeeze both things into one talk. Because I know towards the end of the quarter, you guys might get busier. And we can sort of just squeeze in the essentials, and then the following weeks, if you guys are free, we can, do more qual problems or something. But that's an option unless one of you really wants to give the talk. So just let me know. Both talks aren't so bad. One of them is cup product and the other is Poincare duality. And if you're not proving anything, it's actually quite nice.
I am personally kind of reaching my algebra knowledge and topology knowledge, so I don't think I am qualified to give any further talks this quarter.
You can become qualified,
Qualified. Oh, you joker, John.
Yeah, I'm actually ready to talk about a problem. Do you guys maybe want to think about this one, or do you just want to hear the solution? And
Part 1 was in a previous week, right? Was that like week 0?
Yeah.
That was so long ago, though.
I think Jacob would be able to do part 1.
That's also like very qual experience, You just need to remember stuff you did 5 weeks ago.
That's very true, especially for the other 2 parts of the qual. Like those ones, you just have to recall solutions. So maybe does someone other than Jacob want to tell us how to do part 1?
I actually don't remember what the solution was, so.
I think the hint is just that the cells in the product are going to be products of cells, and the hard part is figuring out what the attaching maps are.
Right, and it ends up just being like all the possible things you can really do, just like one at a time. You sort of take a basis for these attaching maps, corresponding to the basis of your boundary. So maybe Olha can write it down.
So here's what we do. Yeah. So we know that the cell structure of S2 is like 1, 0 cell and 1, 2 cell. This is for S2. So then we do a copy of that, 0 of 2. And then we are kind of multiplying them together to get the cell structure of S2, S2. So structure of our product. First of all, we're gonna have 1, 0 cell. That's the product of our 0 cells. Then for 2 cells, we're also gonna have 2 products now. Whoa. F2, 2, F0. So basically what's happening, we have like this point, E0, F0. And then to that, we're attaching is the sphere, just in case. Okay, we can actually draw this. And like another sphere. At this point, what we already have, I guess, the 2 skeleton of our thing is gonna be the cell structure of each sum of S2, S2. And then finally, our last cell is gonna be, oh God, the product, right? Is that what it should be?
Yeah. And you might want to convince yourself that it's actually a 4 cell. But it is.
Wait, why? Well, I mean, why would you want to do that? Isn't it obvious?
Well, because for a cell complex, right, you need cells, right?
Mhm.
We like, so, you know, this E2 cross F2 has to actually be some n-dimensional cell. It can't be just some product of 2 things. Does that make sense? Like this does end up being a 4 cell. Like if you cross like dn with dk, you get dn plus k.
Right.
You can see it with like the interval, right? Like d1 cross d1, you'll get some sort of square, which is like d2.
So what's the problem again? I'm sorry.
No, I was just saying, like when you're writing down like a cell structure, you have to check that they're actually cells. So like it's not immediately clear why E2 times F2 is in fact a cell, right? Each cell has to be some like D to some power or like some disk.
So you're saying it's analogous to how like a priori it's not clear that a box is like homeomorphic to like a ball.
You're right. Or more so I'm saying that like, you know, just because you have some things that satisfy a property doesn't mean their product will satisfy that property. But with cells, we get lucky because they're disks, and disks happen to satisfy that property.
Oh,
Whereas like spheres, right? Like if you take like S2 cross S2, that doesn't give you S4.
okay. Okay, so like it's the kind of thing that's like worth mentioning, but kind of is obvious, and we're good. Okay. All right, then part 2.
Well, we need the attaching maps, right?
No.
Okay, but maybe everybody remembers what the attaching maps are like.
I think the only really tricky one is the attaching the 4 cell to the 2 skeleton.
Right. So you just apply like the attaching maps one at a time, right? Like on one component it's the identity, and on the other you apply the attaching map from the individual cell decompositions. If that makes sense.
For the attaching maps, look at the Jacobs talk. Reference. Ooh, could you do references on the call?
You can try.
That would be really funny if you were just like, see like so-and-so's notes from their website.
Or,
I
no,
I
see, found the
actually
default solution.
I did this on the call. I referenced Hatcher and gave like the specific name and like probably not page number, but like section. And I think I got some points. It was some problem that had to do with the Hawaiian earring and like, I don't know.
Wait, is that all you gave?
It was part of my incomplete solution. Like I didn't know how to do it fully. So I said some correct stuff and then I gave the reference.
Okay, nice.
And I think I got some points.
Do you want to think about problem 2?
How
One?
I don't understand the notation of this problem. It's a union sub S2. What does that mean?
Oh, that means that, okay, so we're just gluing by the circle or by the sphere, right? So is that what's happening? That is,
Yeah.
right?
So you can think about like D3, you're gluing to the boundary of D3. Right, the boundary of D3 is S2. So you're gluing that S2, and then you have to find some component of S2 inside that product. And this is telling you how you're attaching.
Okay, so I guess what's happening is like to attach this as 2. We're like crashing it together like this, right? And then gluing it together to that thing. To the 2 skeleton, which we know is the batch sum of S2 and S2.
Does that make sense? And then because we have that inclusion, we were able to glue that way. So like the boundary of D3, we're gluing to the product by crushing that great circle and then attaching it to that inclusion for the wedge product or wedge sum.
Yep.
It's probably hard to visualize.
Yeah, I can't visualize that at all.
So the question is, if you have like with the part 1 construction, just that by itself, if you attach like a 4 cell to the 2 skeleton, then does that mean that like that boundary map in homology is just going to be 0 because like there's no 3 skeleton? Or, like,
Yes.
there are no 3 cells?
Yeah,
Yeah.
I guess it doesn't change, like adding something doesn't change the already existing boundary maps, right?
Well, also in terms of cellular homology, we see that if the cells are spaced far apart, right, then those maps are 0. So you're exactly right. Like we only get homology out of things that are attaching like, k-dimensional to k-1. So I think both you and Joss are on the right track here.
Oh, just is writing something.
Yeah, so you can either view this as attaching straight to your cell structure, right? Because they actually give you a really nice thing. So we had some cell structure and we can add a 3 cell, which is just a D3. Or we could, try Josh's idea, which is maybe some Meyer-Vietoris or some long exact sequence. I guess either way, it's a long exact sequence, right? Where we have the attaching maps.
I guess what I was wondering is more like without the 3 cell, it's like, we got something 4, 2, 0, which is like what Olga did with the CP example. And even if you add the 3 cell, it seems like the attaching map for the 4 cell to the 4 skeleton, the 4 cell to the 3 cell is like trivial because because like that image is just landing in the 2 cell or something. I don't know.
Yeah, that's exactly right. Yeah. Because there is, the 4 cell is not attaching to the 3 cell. So there's that, that degree will be 0. That's right.
Let me start probably writing down stuff. So we got, this is for, we got 1 4 cell, got 1 3 cell, this is for 4, this is for 3. For 2, we got 2 cells. For 1, we got 0 cells. 3, 0, 2, 1, 0. Okay, cool. So what Jacob was saying is that like before we added this thing, there was a 0 in here, and this map, which is D4, was 0, and that's not gonna change just because, well, for example, what we could, oh my god, oh, here it is. So for example, if we again look at this composition, then we know that all the boundary maps before from here were 0, which means they're still 0. That just, I guess that's just means that the boundary of this is 0, right? Okay, so this map is 0. Then we also know that, well, we don't even care about this, but we know that since we again have only 1 0 cell, this map is 0. What else? Okay, so now, yeah, what we need to do is, this is still not enough information, so we need to figure something out about this map. Okay, what do you think?
So I guess the question is like, so it's attaching to the 2 cells, and the construction made it sound like it's like the thing you said is like you look at the map into the, like where you quotient all the wedge of the 2 cells or whatever here. So, or just like what's the degree of like S2 mapping to this wedge is like the question, right?
Do you mean, wait,
And right, and we're looking for like a 2x1 matrix, right?
So is it just like A plus B?
So it wouldn't be A plus B, right? Like we're mapping from one thing, right? Like A gets sent to, so like this matrix is like tall, right? Instead of wide as before.
Yeah, sorry, I meant like 1 1. Yeah.
I think that's exactly what it is, right?
Yeah. Because if you think about it, right, like the boundary of this disk is just getting attached to each one of these like wedge summits once. Right, like you took the boundary of the disk, you crushed a great circle, and now you have like one copy of each of these S2s.
Could we like say that G of our, like if G is the additional cell,
Mhm.
and say that the boundary of that is like the sum of those.
It's not this, yeah, like this, yeah, but not the sum
Like
in like a
this
different
one.
sense, right? Yeah, they're like the, yeah.
And that
So
means
like you can write the map as a matrix, right? You can write the map as the matrix 1, 1, like the tall matrix.
isn't that the same thing?
Yeah, it's the same thing.
Which is gonna mean that, what is it gonna mean? I guess the only thing that we need is that this map is injective. Its image is like isomorphic to Z, and its kernel is trivial, which follows from that being injective, right? Yeah, so now we're ready to actually compute our homologies. I'm gonna do it here. Okay, so the fourth one of W is with quotient. Oh, that's just E. I don't have space for that, but whatever. The third one is with quotient, okay, right here. 0, which is the kernel by 0. So we get 0. The second one is gonna be like Z2 quotient by Z, which is Z. And then H1 is gonna be just 0. And finally, H0 is gonna be Z.
So this problem sort of shows the power of this cellular homology, right? Like if I just told you this space, like S2 cross S2 and then glue it to D3, it could be hard to compute the homology, but it's almost trivial once you have some cell structure on it, especially if you know like how it's attaching.
So question I have about this problem is, it seems like adding the 3 cell is like kind of imposing a relation, like when we were talking about Van Kampen, Sieber Van Kampen, like
Yeah, that's exactly right.
so is that true in general? Like if you already have a CW complex, or maybe even in general, if you had like some space, no, I guess maybe CW complex, and you attach like an N cell to the N-1 skeleton, and does
Yeah.
it always just have the effect of like imposing an additional relation on that?
Yeah, so if Olha goes back to the sort of towards the start where she wrote the properties down for these, there were 3 properties for this like HK of relative and it's the start of like the cellular stuff. What you said is exactly right. Like we could, okay, yeah, this one. So the third one here is saying exactly that, right? Like if we're looking at the homology, which is lower than the skeleton, then it doesn't care about higher cells because those relations are adding relations for higher homologies. And if we're looking at the nth, like at the right level, then we're at least surjective, but we might have less, right? Because like we might have additional relations if you look at the skeleton of one above it. So this is exactly the same as Van Kampen's, right? It's saying like, you know, like if you're talking about fundamental group, you care about the 2 cells that could add relations, but you're generated by the 1 cells and then you might quotient out by more stuff. So this is exactly the right way to interpret this. This third property in the lemma is saying exactly what you explained.
Gotcha.
Yes, so I think I'm not gonna go into more problems because it's been 2 hours. But I don't know, do you want a list of the problems that Elon gave me?
Yeah, maybe you can send them out.
Oh, I know what, I'm gonna just add them into my notes when I'm gonna send them.
Okay, perfect. Let's thank Olha.
Thank you.
Thank you.
Yeah, great talk. So these can be free points on the qual. Like we see the computations often aren't super difficult. So that's the goal, right? One problem at a time, you guys will pass the qual. Okay, cool. Thank you.
Thanks. Thank you, Elon, especially. Okay, bye, guys.
Yeah.
So if you're still recording, by the way. But if you upload the video